righty then. Welcome back to the world of physics, the WOF, and it's pretty rainy here where I am. My name is John Frensley. I teach at Prosper High School. It's about 30 miles north of downtown Dallas, and I don't think you can see me right now. I'm watching myself on my little live view here. On my phone, and so you're not missing anything. Oh, yes, you can see me. Okay, well, there you go. I know I have a face for radio, don't I? This is going to be about power. I'm going to be completely honest with you. This is not really a topic that is front and center in AP Physics C or either in AP Physics 1. Power really becomes more important when you do circuits, and so if you're in electricity and magnetism, then you're probably going to study it quite a bit. P1 isn't going to do circuits this year. Physics C mechanics, I mean, it's very tiny. When you see my list of review problems, it's like 2 problems, and it's the only 2 problems I could find that have had the word power even show up in it. So here's the deal. First of all, if you're from Physics 1, about the first 10 minutes are going to matter to you. But if you're from Physics C, I do have good news, and that is this. I'm going to use this as a reason to practice you on the kinds of problems you might see on this year's exam. Remember, Physics C is mostly about mathematical derivations and drawing graphs and free body diagrams, things like that. Well, you can't do that on this year's exam because this year's exam is supposed to be answered like by typing into a text box. So I'm going to use this subject of power not just to review you on power, that's going to take me 5 minutes to do, but to show you, okay, if I can't do math, and instead I'm going to do like an argument, then what's that going to look like in Physics C? So that's really going to be the main focus, with power being kind of the backdrop of that, right? Okay, so here's an example warm-up. So we got at time T1, a skydiver falls through the air at terminal velocity without his parachute open. At a later time, T2, the parachute is open and the skydiver falls with a different constant velocity because, get this, the parachute's open, right? So you're going to do parts A, B, and C. And for this, I would encourage you to open up a little word processor on your computer. If you're on a Windows machine, you might open up Notepad. If you're on a Chromebook, you might open a new tab with a Google Doc or something like that. On Apple, just open up some kind of word processor where you can type. I want you to practice typing answers to these. So part A, at which time is the force of air resistance on the skydiver greater in magnitude? 1, 2, or are they both the same? Justify your answer. B, at which time is the power delivered to the skydiver by the weight force greater? 1, 2, or are they both the same? Justify your answer. And at which time is the net power, and it might be different, delivered to the skydiver greater? 1, 2, or are they both the same? So I'm going to give you 2 minutes. I want you to type the best answer that you can, address all 3 parts, and here's your 2 minutes on your mark, set, go. normally, like always, we're going to answer this little go to it, our little warm up later on after we do our little discussion here. So here's the overview. We're going to define power. Whoa. We're going to relate power to energy, force, and velocity. It's going to take us 5 seconds. I mean, you just watch. But here's the big one for today. We're going to use this thing with power, and my goal is not so much to teach about power, because that would really take me 5 minutes to do. So I want to show you problems related to power that are of the type that you're going to see on your Physics C exam, where you have to compose a scientific argument. So yes, this Physics C exam is going to feel like a P1 or P2 exam, where it's all this writing, but it's still going to test Physics C learning objectives. So that means that a P1 student will not necessarily be able to do it, right? It's not just going to be a P1 exam with this letter C slapped on it, right? Here's what you need to know. Okay, power is the rate at which energy changes forms, right? So if I have, let's say, a 100-watt light bulb, that means 100 joules every second of energy is going from electrical to light. It's changing forms. Energy doesn't get used up. I mean, when we say it's used up, it means we just change it from one form to another, right? When I use gasoline, I change the chemical energy into kinetic energy, right? But how rapidly does that take place, right? So symbol for power is capital P. The units are called watts, named after James Watt. He was a steam engine guy. And then the equation for Physics C is power is the derivative of energy with respect to time, dE dt. If you're from Physics 1, it would be delta E over delta T. In calculus, we use D rather than delta. It serves the same purpose, right? Okay. Now, each individual force that acts on an object is going to perform work. So this is a review back to talking about work. So each force, so if I have 5 forces acting on me, then I'm going to have 5 amounts of work. Now, some of those amounts of work may be positive, some negative, some zero, but 5 amounts of work, 1 from each force. And so each amount of work is going to give or take away energy from an object. And so I didn't use W here. Instead, I used dE, or if you're in Physics 1, delta E, right? E is force dot dx or delta x. For Physics C, remember that the dot product means that you are taking the component of force that's parallel to the delta x, or in other words, it's force times the delta x times the cosine of the angle between them, right? So you're going to get a lot of positive work if F and your displacement dx are parallel or close to parallel. No work if these two are perpendicular, these two vectors. If these two vectors make an obtuse angle, then your work is negative, and you're having, and that force is trying to take any energy away from your object, right? So if each individual force performs work, then each individual force is going to deliver power to the object. So each individual force is going to give you a delta E, which is work. Then each individual force is going to give you delta E every second. That's power. So what I've shown here is the power from a specific force is the work it does over time. So dE dt. So I just plugged in my dE here, which is force.dx. And look, I've got dx over dt. So that's really just force times velocity. So this is the shortcut to calculating power. If I ever ask you for the power delivered by the gravity force, you would just take the gravity force and you would dot it with the velocity of the object. Now watch out, that's a dot product between two vectors. So if an object is moving sideways and the force of gravity is down, that's a right angle, and the dot product gives you nothing, because the dot product means cosine, and the cosine of 90 is 0. However, if I have an object moving straight down and I ask for the power delivered by the gravity force, then the dot product, the cosine of 0 degrees, is 1. And so then I can just do the force of gravity times the velocity. Okay, now what about net power? Net power is the sum of each individual amount of power, just like net work is the sum of each individual amount of work, right? So I'm going to say the net power is the sum of each individual power from each individual force. If I have 8 forces on me, I have 8 amounts of power being delivered to me, right? So then I plug in my F dot V. Remember, that's vector F dot vector V with a sigma. But watch out what happens here. On the next step, I factor out the V. The object has the same velocity in every single one of these terms of the summation. The force vector is different. It might be weight, normal, friction, tension, the spring. Like there could be those 5 forces acting on me, right? And so we're going to do each of those forces dot V, but then I factor out the V because the V was the same V in all the terms. And what is the sum of each individual force? That's the net force. So you want the power delivered by one force, that one force dot V. You want the net power delivered, it's the net force dot V, which would be MA, A is a vector, dot V, V is a vector. That would be your net power. So we're going to use that idea as we go along here. Just so you know, everything that I just said can go for rotation too. So what about in rotation? Well, instead of force dot dx, work is torque dot d theta, right? You just replace force with torque and x with theta, like they are the analogs of each other, right? And then I might say power is work over time, dE over dt, right? Okay, all good. And then, okay, never mind. So my guy from the College Board texts me like he knows I'm in the middle of a session. Why does he need to text me in the middle of the session? I wonder if he's watching right now. Okay, so torque, and then we have d theta over dt instead of dx over dt. That's just omega. Okay, all good. And then same goes. So it's now the net torque times omega. So instead of force dot v, it's now torque dot omega. Okay, all good. Isn't that funny? Okay, so either way, this is important. The net work done is the change in kinetic energy of the object. The net work done is the change in kinetic energy of the object. So that means that the net power delivered is how rapidly the kinetic energy is changing. So if my car engine can produce 10,000 watts of power, that means my car is gaining 10,000 joules of kinetic energy every second, if that's the net power. Now, of course, we'd have to factor in friction or air resistance or other things like that. Okay, that's really all you need to know. So let's go back to our little warm up here. And this is going to be about the last thing that anyone who's watching from Physics 1 is going to care about, because after this is going to be really physics-y stuff. All right, so part A. At which time is the force of air resistance on the skydiver greater magnitude, or are they both the same? Okay, so get ready to kick yourself if you got tricked by this one, because I'm serious. So I teach forces first in P1. So this is on my first test in P1, and it kills everyone. Okay, I get the lowest right answer return of all the questions on that first test, and students are just kicking themselves afterwards. Here's the reasoning. Ready? At T1, this is without the parachute. At T1, the skydiver's velocity is constant, right? Because he's terminal velocity. So the force is balanced. The air resistance equals mg, right? Now, what about at T2 with the parachute open? The guy's going much slower, but he's going a much slower constant velocity. So at time 2 with the parachute open, it may be a different velocity, but that doesn't matter. What matters is that the force is balanced. So now the air resistance force is again equal to mg. So it turns out that both air resistance forces were the same number of newtons. Even though the speed is different, the air resistance force was equal to the weight of the skydiver when he was free falling terminal velocity with no parachute and falling terminal velocity with a parachute. All right, I hope you don't get messed up on that one if they have it on your free response coming up here in 2 weeks or however long it is. Okay. At what time is the power delivered by the skydiver by the weight force the greatest? So here's what I'm thinking. I'm thinking power is force times velocity, right? So I'm only going to look at the weight force, though, because this is the power delivered just by the weight force. So I'm going to say the force is mg and the velocity is v. Well, now I know for sure that the mg of the skydiver is the same during the entire skydive. You're not going to suddenly lose weight during a skydive, right? There's no treadmill up there, all right? But the velocity is greater when he has no parachute open at time 1. Same mg, greater velocity at time 1. So the power delivered by the weight force is the greatest at time 1, right? Now, let's talk about part C. At which time is the net power delivered the greatest? Well, net power is the rate at which kinetic energy changes, right? So you have a net power if your kinetic energy is increasing or decreasing. Well, at time 1, that the velocity was constant because he was at terminal velocity. And at time 2, he was at a new terminal velocity, but the velocity was still constant. So at both times, the velocity was constant, maybe a different velocity, but that doesn't matter. It was constant. So the kinetic energy was constant at both times, and that means the power delivered was 0. The derivative of a constant kinetic energy is 0, or the rate of change of a constant is 0. Yep, that was the go to it there. Now, if you're a teacher and you're watching, I'm going to level with you. So, and you're going to see me do this on my Facebook site. So if you haven't, if you missed last Tuesday, I'm going to peddle my Facebook site again. So I've looked through the practice questions on AP Classroom that they published for students. And my motto is what's good for the goose is good for the gander. So what do you mean when you say that, Friendsley? Well, this question appeared on the electricity and magnetism practice questions. So what I did is I retooled it for mechanics. So I feel like if there's a physics E&M question that could be rewritten for mechanics, mechanics and test the same skill, I'm going to do it. And if you note on my Facebook site, I'm going to start putting up questions like questions for physics 2. And you might say, wait a minute, this is the same skill as this E&M question that the College Board wrote. You just kind of tweaked it a little bit to make it legally distinct. Yeah, I'm going to do that because I want to give everybody the maximum practice that they can get. So what we got here, this is a graph that shows the net power delivered to the skydiver between time equals 0. Let's let time equals 0 be the instant that the skydiver just started falling straight down from rest. So let's say he didn't jump out of an airplane. He just jumped off a building, right? Some stunt guy, right? All right. Now, to time equals T1, which is when he reaches his terminal velocity before the parachute. So this is way before the parachute. Time 0, he has just started falling straight down. Time T1, he has reached his terminal velocity before pulling the parachute. The graph starts at 0, increases to a maximum, then asymptotically approaches 0. Your job, you get 3 minutes to do this, and you're going to type in your little word processor to practice what's going to feel like doing it on the real exam. In a clear, coherent, they're probably not going to use this language on the C exam because it's AP Physics 1 and 2 language, right? But same idea, right? In a clear, coherent paragraph-like response. Why does the graph do this? Start from 0, increase to a maximum, and then decrease asymptotically back to 0. You get 3 minutes on your mark, get set, go. All right. Yeah, it turns out Mr. P from the College Board is watching. And so, Mr. P, I am going to take all of your questions that are on AP Classroom for practice for Physics C mechanics and EMAG and 1 and 2, and I am going to retool them for the other subject areas like you see here, and there is nothing you can do to stop me. I want everybody to get the maximum practice possible. Okay, so why does the graph look like this? All right, well, I'm going to start, and notice I'm going to have a set of bullet points here, and I want you to grade yourself, okay? We don't have to share our grades grades with each other, but I want you to see, if you really tried to put effort into composing something really good, how many points did you get, right? So I'm going to start with this. I'm going to say that the net power is P equals FV, and you don't have to put the little nets if you don't want to, just P equals F times V. Now, here's what I'm thinking. I'm thinking at the beginning, there ain't no V. The guy dropped from rest. So of course the power would start at 0 if the V starts at 0, right? So we start with no V, we start with no P. Pretty straightforward, right? So give yourself 2 points if you got those 2 points. Now, what's going to happen over time? What's going to happen over time is that the velocity is going to go up, but the net force is going to go down. If you look at my nifty little animation here, you'll remember it from our drag force discussion a week ago. You'll see that the velocity increases to a maximum. I didn't redo the animation with the words net force here, but you know that net force and acceleration are directly proportional. That's Newton's second law. Thank you very much. So just replace the words acceleration with net force, right? And just say to yourself, hey, the net force is asymptotically approaching 0. So we start with 0 velocity, 0 power. Then as the velocity goes up and the net force goes down, we're going to kind of pass some point where together they multiply to a maximum amount, right? Turns out, you don't have to have this written, but this is just a factoid. It turns out that the maximum power takes place when velocity is halfway to the end and net force is halfway to 0, right? So wherever the velocity is halfway to its asymptote and net force is halfway to its asymptote, that is when the two quantities, force and velocity, will multiply to the most that they're ever going to multiply to. I don't feel like you had to put that stuff in parentheses, but it would have been nice to hear you say, hey, at some point, force and velocity multiply to a maximum because one's on its way up and the other one's on its way down. And then, of course, after a long time, the net force is asymptotically reaching 0, which means that the power is asymptotically reaching 0 because power is force times velocity, right? Now, ask yourself this question. If you didn't score a lot of points, ask yourself, was it really that difficult, though, now that you're looking back? Was it really that difficult to come up with this argument, or did you make this harder than it needed to be? I'm going to tell you that the students who struggle on this exam, just like the students who struggle on P1 and P2, are students who make it harder than it needs to be. So just step back, sit back, relax, and just say, is there a really easy way to explain this? And I want to get all my thoughts on the page, and I want to get them organized, but I don't want to overthink it and think that it's some big, terrible puzzle, right? Okay, so now let's check for some understanding. If you're still here from AP Physics 1, go away, because this is probably not going to apply to you, all right? We're going to get into some parts that are going to deal with some calculus-y stuff, right? So student suggests that if you were to place a cart, mass M, with frictionless bearings on an incline, angle theta, we see the picture of it right here, okay, and you release it from rest, a constant net power would be delivered to the cart. So here's your job. Your job is to tell me, is this student correct? Is that a valid statement that a cart on a flat incline, or a straight incline, not a flat one, is going to have a constant net power delivered to it? I want you to explain your reasoning. Again, I don't think the Physics C exam is going to use this language, but you might as well pretend like it uses this language if you took P1 before this or P2. Explain your reasoning, clear, coherent paragraph length response. You can get 3 minutes, type in your little Word document or whatever. Practice formulating these arguments for your C exam. On your mark, get set, go. Okay, so here we go. That was 3 minutes, and I'm hoping that after you see this rubric, you'll realize it probably would have taken you about 30 seconds if you knew what you were doing. So again, don't overcomplicate these things. Everything is going to be simple. It's just your job is to see through the hogwash, right? Okay, so is an incline constant power? Well, here's my argument. One, let's just start with an equation. P equals F times V. I feel like on this exam, you're going to be typing. You're not going to be able to do subscripts or superscripts. So maybe you just put P equals FV, or you just say the net power is P equals FV and don't worry about putting any little subscripts or whatever. Now, I'm going to say the net force is constant. Now, maybe you forgot that the force on an incline, the net force is mg sine theta. If you forgot that, then just don't write it. Just say the net force is constant. So if you forget something, act like it's not important and don't mention it. But if it occurs to you, please put it in there somewhere. So if you're like, hey, I know that the net force is constant. I happen to know that it's mg sine theta. Put it in that little text box, will you? Here's another clue. I don't know how to type theta on a keyboard. I mean, unless you live in Greece, I suppose, maybe you could. But the AP exam this year for Physics C, and I think for the other physics as well, is going to say you're allowed to use different symbols than you're used to. So here's an idea. Use the at sign. Just say, I'm using the at sign, shift 2 as the angle, okay? Or you can spell it out, THETA or ALPHA for alpha or whatever. Use the ampersand, shift 7 or whatever kind of thing. The reader is going to try and understand what you're talking about. Just please, if you use a weird symbol, say that I'm using the dollar sign for the angle or whatever. Okay, all good. Now, the net force is constant. Okay, that bodes well for constant power, but the velocity isn't. The velocity increases with time because the net force is constant. If you have a constant net force, you're going to have a velocity that accelerates, right? Duh. Okay, you're going to have an acceleration. So I'm going to say the power delivered is going to increase with time, not stay constant. And for some reason, my text boxes are behind my picture. I apologize. The picture's out in front for some reason, but you get the idea that the power delivered is not constant. And again, I did a little math. That's really just for trivia, right? You don't need to do all that math. I feel like you would get all the points if you just said power is FV. The F's constant on a straight incline, but the V must be increasing because you have a constant force. So if the V increases, the P increases, right? That's not a constant power. Yeah, what you're seeing there, that's not a constant power. The power is increasing every second, right? Isn't that crazy? Power is the rate at which energy is delivered, and the rate at which energy is delivered is increasing itself. It's a rate that increases, right? Crazy, right? I know. Now, I'm going to give you 3 more minutes. Let's look at these. Here's 2 inclines. So the flat incline did not give us power, a constant power input. So which of these inclines might? Would it be incline A that could have a chance of giving us a constant power, or is it incline B that could give us a constant power? Now, let me just tell you, okay, it's like Star Wars. Use the force. If one of them feels like a right answer, it's probably the right answer, right? I tell my students, if something feels right, it's a 95% chance it's right. And you need a specific articulatable reason why you're going to talk yourself out of what feels right on a physics exam. So if it feels right, go for it. But now the tricky part is using appropriate physics language to say, why is this thing that's right? Right. Okay, here we go. You got 3 minutes. Type in your little type box on your mark, get set, go. that's the end of that. Okay. I'm hoping that you're thinking a constant power input. If a straight incline gave us an increasing power, then maybe we should have our incline become less and less and less steep to give us a constant power. Since this makes power increase, then you'd probably be right. But can you explain it using equations and relationships? That's all we're doing here in physics, is explaining with equations, which are themselves relationships, and with words to explain how the relationships work, right? So give yourself, I don't know if this is 4 or 5 points, but see how many points you can get. Let's start with our favorite. Power is force times velocity, right? Now, here's what I'm thinking. If power is going to stay the same, then if velocity increases, then we need force net to decrease, right? So on either incline, the object is going to speed up, right? Both the objects are going downhill. They're going to a lower height. So you're changing potential energy into kinetic energy, right? So either way, they're going to speed up. But if the V increases and the P needs to stay the same, the force needs to decrease. The net force has to decrease with time, right? So either way, the velocity is going to increase. We need the net force decrease with time. Well, on an incline, the net force depends on how steep the incline is. So if the net force is going to decrease, then the steepness of the incline needs to decrease. So net force on an incline depends on how steep the incline is. So the incline must get less steep as the cart goes. So incline A is going to do a better job of meeting this requirement. And in case you honestly care, it's actually a very specifically shaped incline. It's a function of the form of like y equals a constant minus another constant x to the 2/3 power. Yes, I know there's some physics teacher out here is like, wait a minute, and then they're going to go back and they're going to listen to me say that again. Y equals some constant minus another constant x to the 2/3 power, and they're going to graph it in their calculator. And sure enough, what you'll see is you'll see it getting less and less steep as it slopes downhill. So did you get all 5 points? Even if you didn't, this is for practice, right? And this is for learning how to see through the ridiculousness and see through the smoke screen and just say, hey, this is what I know is true. And this is the basic relationship that underpins it, equation or whatever. And then this is how the quantities are changing or not changing or things like that. Okay, so now we've decided that incline A is the best incline for making a constant input of power, right? So this is the incline where the net power could be constant, right? Now, fill in the blank. If the net power is constant, delivered to that car, then the incline has to be shaped a special way. I just said that the parent function of the incline is actually, you'd never be asked to do that, even on a regular physics C exam. As the cart rolls down the incline, something remains constant. So this is like kind of a multiple choice, but it's a multiple choice where you're going to justify your answer, right? So as you roll down the incline, if there was a constant power input, which of these 4 things would be the thing that stays constant? And then you're going to justify your answer. So you're going to choose one of them. Then you're going to say, here's the basic physics that underpins it. And this is how that basic physics applies in this situation. All right. So here you go. 3 more minutes to practice this. Use your little Word document that's open in front of you on your mark and set go. I'm going to tell you right now, this is a misdirection. When I talk about the term misdirection with my students, a misdirection is a problem that tries to trick you into thinking about this when you should be thinking about that, where that and this are equal. This shows up a lot with conservation of energy and conservation momentum. Tell me about the momentum after the collision. No, I'm going to tell you about the momentum before the collision because those two things are equal, and it's easier to talk about the momentum before the collision. Here, the trick is this. You ask yourself, there's a constant power delivered to this cart. What does that mean? That means the cart is gaining the same kinetic energy every second. But don't think about kinetic energy. Ask yourself, where does the kinetic energy come from for this cart? I don't see any springs or gasoline. It's got to come from potential energy. You see, gravitational potential energy. So you're supposed to think if the energy transfer is constant, the same joules every second, then you could say you're gaining the same kinetic energy every second, but that's not going to help you get the answer. Instead, you're going to say, I'm going to lose the same potential energy every second. So that's where we got to start off. We got to start by saying, when the cart's on the incline, the kinetic energy that it's gaining every second comes from losing gravitational potential energy every second. So the net power is how much kinetic energy you gain every second. If that power is constant, then you gain kinetic energy at a constant rate, you'll lose potential energy at a constant rate. Well, what does that mean? That means that if you lose potential energy at a constant rate, you must be dropping down the same number of meters every second. You're not changing M or G. So if you lose the same joules of potential energy every second, then you lose the same height every second. And if you lose the same height every second, then that is the vertical component of velocity. So the answer was, in fact, B. Vertical component of velocity is constant. And here's a 5-point reason why. So again, ask yourself, is this something that you did? If not, is this something you could do if you just clear your mind and just, make it, don't believe that it's this big scary monster, but that it could be something easy. Okay, here's the last one. This is the final boss. You're going to get 4 minutes for this one. Now, I'm going to warn you. One of the reasons why this particular C exam is going to be tricky, the thing that makes physics C is, you guessed it, the C is for calculus, right? Well, it turns out they can't make you show a bunch of math because that's not the way the exam is formatted. It's purely text. So instead of doing calculus, you might have to talk about calculus. So here we go. We've established that a constant acceleration is not a motion that has a constant input of power. Those two things can't happen at the same time. So let's say you have this hypothetical student, right? And the student says, for motion with a constant input of power, the motion has to be modeled by x equals a constant t to the 3/2. Notice that's not a constant acceleration because that has to be t squared for a constant acceleration. T to the 3/2 where c is a constant. Is this student correct or incorrect? Again, use the force. But then you got to tell me how x equals c times t to the 3/2. Focus on that exponent, t to the 3/2. How is that going to tell me whether this is constant power or is not constant power? You get 4 minutes for this big one. On your mark, get set, go. that's enough of that. Okay, so what's going to do the argument for us here is the exponents. It's not going to be the coefficients. So I'm going to do some calculus, but notice I'm only really going to work with the exponents here. For example, I say a position is constant t to the 3/2, then velocity is going to be a different constant t to the 1/2. It's going to be 3/2 c t to the 1/2 because you multiply by the power. I know. I don't care. I only care about the exponent, okay? So I'm really only making an argument with the exponents, all right? I put C2 for you just to show it's a different constant, right? Now, this is because position velocity with respect to time. Now, if I take another derivative, then I get acceleration is something t to the negative 1/2 because you take one away from the power. I don't care what the coefficients are. They're not going to do the argument for me. The exponents will. Now, because net force and acceleration are directly proportional, then the net force is a constant t to the negative 1/2. So velocity is something t to the positive 1/2. Net force is something t to the negative 1/2. So if I do force times velocity, the t to the negative 1/2 that force has and the t to the positive 1/2 that velocity has will cancel out, and I'm left only with constants. Yes, it's going to be the 3/2 and the 1/2 and the negative 1/2 and then math and then. I don't care what the constants are. All I care is their constants. So the time factors cancel out, leaving only the constants. Okay, brief summary. Power is the rate at which energy changes forms. The symbols P, the inch/watts, P equals dE dt. Each individual force does work. So each individual force delivers power. That force dot product, the velocity of the object, is the power delivered by that force. The net power is the net force dot vector dot product, the velocity, right? All good. That's all you really needed to know. Here's the deal. It barely shows up on the AP exam. This is one you can skip, honestly, in my opinion. So I'm happy if you watch this, but you watch this not to learn about power because it's almost certain you're not going to be asked it. You watch this because you wanted to see how questions might be asked you on your Physics C exam. Typing only type, conceptual. How can Physics C be conceptual? It's calculus. Well, you saw it here first, America, and the rest of the world. So these two problems are the only ones that even use the word power, except for ones in electricity and magnetism and thermodynamics that I'm not including, right? Because that's not Physics C, right? Okay, I just wanted to give you a little plug again. I know that we're after time, but remember, I have my own Facebook page. You don't have to have a Facebook account. You don't have to pay any money. Just search Friendly Physics Facebook on Google. Every day, 4 problems, one for P1, one for P2, one for C Mechanics, one for CE Mag. It's posted every day at 8 a.m. Central Time. The scoring rubric where you can score yourself is the next day at 7 a.m. Central Time, right? All questions are meant to be answered through text only. These are questions that I have either composed myself or I have modified them from old AP exam questions, or even AP exam questions from AP Classroom or whatever. Sometimes I've taken an EMAG question and changed it into a Physics C question because it's the same mathematical model but a different topic or something like that. Please note that sometimes the P1 question says it may overlap with mechanics. The mechanics question may say it may overlap with P1. I will only put that if there is a way that they can overlap. So if the mechanics question has calculus, it will not ask P1 students. It won't say it overlaps with P1. Same with P2 and CE Mag, right? It won't say it overlaps if the P2 question is magnetism, because even though that's technically E&M, it's just not this year's exam. This is specifically for this year's exam. So you can see right here that the Physics 1 question overlaps with C Mechanics. The Physics 2 question overlaps with EMAG because it's about charges, right? But the mechanics and EMAG questions don't overlap with P1, so it doesn't invite you to do that. And then here's what the solutions look like. This was for April 15th. All right. Well, I hope that you enjoyed our time together studying this topic that's probably not going to be on your exam, but a skill that will certainly be on your exam, right? So I'll see you next time. We're going to start doing momentum, I believe, next week. Isn't that fun? See you there, fellas.